So what we're doing today kind of puts together couple big ideas we've been talking about over the last couple weeks. First one is, what does it mean what do we mean by an infinite sum? What we do is we take a finite sum and then we take that n and run it off to what? Infinity, okay? What we did on Monday is we talked about nth degree Taylor polynomials. Nth degree Taylor polynomials where extensions of the tangent line up to the nth degree So if we wrote this with the sigma notation, it was the sum k goes from 0 to n of the kth derivative at a over k factorial times x minus a to the k. And so what we can do, then in the meantime, on Tuesday and Wednesday, we talked about power series. So we talked about functions that were defined like this. And in the cases where we had geometric series, or in the cases where we had like the arctangent, which we could get by integrating a geometric series, or like the case of the natural log, which was the video that you can get by integrating a geometric series, when we would look at what's going on graphically, we noticed that when we did the partial sums, they were converging to the function in the same way that these Taylor polynomials were. You follow? In other words, the partial sums of the power series seem to be doing the same kind of thing that the Taylor polynomials were doing. You with me or not? So what we're going to do today is going to combine this idea that we had with infinite series with this idea, Taylor polynomials, to give us Taylor series, and then we can investigate Taylor series as specific examples of power series, and then realize that power series really are all Taylor series. Okay, so that's kind of the idea. That's our definition. The Taylor series T of x is defined as, or you could put like a little letter a here if you want to indicate the center. It's the limit as n goes to infinity of the nth degree Taylor polynomial, which is the limit as n goes to infinity of the sum k goes from 0 to n, the kth derivative at a over k factorial x minus a to the k, which, when in doubt, write it out. It's f of a plus f prime of a times x minus a plus f double prime of a over 2 x minus a squared plus dot, 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 and it just goes on forever. And so the idea behind a Taylor series is we're trying to grow the function by knowing everything about a. F of a tells you the y value on the graph. F prime of a tells you the slope of the graph at a. Now, when you get to the slope of the graph at a, that tells you a little bit about what's near a. You follow? It tells you what the graph's doing. Is the graph kind of doing this, or is the graph kind of doing this, or is the graph kind of doing this? The second derivative tells you about what? Think back to Calc 1. Second derivative tells you about concavity. So, is the graph doing this? Is the graph doing this? You with me or not? So, what we're trying to do is we're trying to sculpt the function by knowing everything that happens at a. Follow? So, and in some of these cases, in the case of sine, cosine, e to the x, we're going to be able to recover information about the entire function everywhere by just knowing everything about what goes on at 0. And that is a mind-blowing idea. That if you know all the derivatives at 0, you know exactly what's happening everywhere with the function. To me, that's a pretty cool thing. That's the ultimate of, because calculus is normally looking at things locally, and the mean value theorem helps you turn local to global behavior. This is the ultimate, knowing what's happening at a point, telling you what's happening everywhere. That's the ultimate local to global phenomenon. So let's do a couple of these. Find the Taylor series. Oh, I guess we should point out here, in the special case when you're centered at 0, the Taylor series centered at 0, typically called Maclaurin series. Maclaurin and Taylor are they're the names of two mathematicians. Maclaurin series is when you have your Taylor series centered at 0. All right, find the Taylor series for the given functions and state the interval convergence. So we start off with f of x equals sine of x, centered at a equals 0. So AKA, this would also be called the Maclaurin series, since the center is 0. So how do we do it? So T of x is equal to the sum. K goes from 0 to infinity. The kth derivative at a over k factorial x minus a to the k. If we look at the center at 0, for a equals 0, then that's the Maclaurin series. We'll call that m of x for Maclaurin. K goes from 0 to infinity. Everything's at 0. So I'm a big believer in, when in doubt, write it out. Let's just start taking derivatives, plugging in 0, building the terms, and see if we can find a pattern. Okay? So I don't care how you organize this. I typically use like a little chart. So I'm going to make a little chart. And I'm going to have k here, 0, 1, 2, 3, 4, 5. And I'm going to have the kth derivative of x. And I'm going to have the kth derivative at the center, which in this case, we're centering things at 0. And then I'm going to have the kth derivative over k factorial. And then I'm going to see if I can find a pattern. You with me or not, folks? Okay, so I can use these. So these are the coefficients, right? And then I'm going to have the x to the k. All right, so we start off the function. Remember, with this notation, the 0th derivative is the function where I've taken no derivative. So it's just the function. So it's sine of x. And now we go back, as is our custom, now we start taking derivatives of sine. Derivative of sine is cosine. Derivative of cosine is minus sine minus cosine, sine, cosine. And of course, as has been the observation way back in Calc 1, the derivative cycle for sine repeats every 4, right? Every 4 derivatives are going to be the same. We'll talk more about that on Monday when we tie it into something else that has a cycle of 4, which seems completely unrelated. Okay, so you take the derivatives, and once again, how many derivatives do you take? I don't know, as many as you need to see the pattern. Everyone's different. Okay, maybe you need to go down to the 7th derivative. Then you evaluate all those derivatives at the center of the series. In our case, we're doing the Maclaurin series. The center is 0, so I plug 0 in. So you plug in 0. And you get those things. You with me or not? Okay. Now, I do this. I take 0 over 0 factorial. And remember, don't freak out, because 0 factorial is the number of ways to arrange nothing. And there's one way to arrange nothing. You just leave it as is. So this is 0. That's totally cool. I got 1 over 1 factorial. I got 0 over 2 factorial. I got negative 1 over 3 factorial. I got 0 over 4 factorial. I got 1 over 5 factorial. You with me or not? Now notice there's no cancellation happening here with these things. They are what they are. And now I just multiply it by the power of x. Well, 0 times anything is what? 0. 1 times x to the first. That's just x. 0 times x squared is minus 1/6 x to the third. What's 0x to the fourth? And then 1 over 120 x to the fifth. You with me or not, folks? And so my Maclaurin series for sine x is looking like x minus x cubed over 3, or excuse me, x cubed over 6 plus x to the fifth over 5, it's 5 factorial, 120. Now this is how you can tell if you see the pattern. Can you tell me what the next one would be? Would it be plus or minus? Minus. What would the power on x be? 7. And what would the denominator be? Well, let's look. That's a 1 factorial, 3 factorial, 5 factorial. So the next one would be what? 7 factorial. What would be the next one? X to the 9th. It would be positive over. All right. So if you can start guessing the next one, that means that you get the pattern. You with me or not? Okay, now I want to codify that pattern. So what do you notice about all of these exponents? They're all what? They start at 1, and then you're always doing what? Yeah, you're always adding 2, right? They're all the odd numbers. You follow? So, let's try to do this here. K equals 0 to infinity. I've got x. They start at 1, and they go up by 2 each time. So we could, if we wanted to, we could just think back to arithmetic sequence days. Or we can just remember that if you start at 0, the odd numbers are generated by the 2k plus 1s. Is that okay? And what do we notice about what's going on down here? This was 1 factorial. This was 3 factorial. This was 5 factorial. So notice that the exponent here matches the what? So down here would be what? 2k plus 1 what? Factorial. And now all we have to do is incorporate the plus and minus. And how do we get pluses and minuses? That's from a power of -1. So let's look at -1. And let's start with -1 to the k, and let's see if that is the correct one. Because it's either going to be -1 to the k or -1 to the k plus 1, depending on if it starts off as a plus or a minus. You follow? Does this work when k equals 0? Does that give me a plus or a minus? Plus, when k equals 1, plus or minus? You follow? Makes sense or not, folks? And once again, what's the ultimate check? When in doubt, do what? Write it out. Okay, just write it out so that you get the same thing. So that's our Maclaurin series. So let's take a look at this. Let's fire up Desmos, as is our custom. The Maclaurin series, by definition, is the Taylor series centered where? At 0. So what do we expect to see? Remember, these are the, we're taking the partial sums. We're taking the Taylor polynomials. Now it's x minus 0. I'll just be pedantic. It's really just x to the, once again, 2k plus 1 over 2k plus 1 factorial. is. Now, once again, our slider for n's going to start at 0, go to, I don't know, 50 with a step of 1. So make sure when you do this, you tell Desmos that you want n to be a step of 1. Otherwise, it'll do like crazy stuff and put like a half in there. It'll mess up. Okay. But here we go. Well. When n equals 0, it's just going to give us our first term, which is x, which is the tangent line. And here we go. I'm going to zoom out on the x-axis. What's happening? Isn't that wild? Because once again, we're using information only at 0. Right? And we're recreating the entire curve everywhere based on just what we know at 0. That's, we knew that differentiable meant locally linear. That was the mantra in Calc 1. In fact, we just used it again today. Calc 1, we talked about Newton's method. I said, okay, f is differentiable. What's that mean? Functions locally what? And they all said linear. Yep. What's that mean now? But this is showing you that if you know not only the derivative, but if you have all the derivatives and you know them all about what's happening at just one point, that's enough information for you to shape how the thing is going to spread out from there. So it's kind of like you know exactly everything happens, 0, boom, and then it spreads out from there. And if you know all the derivatives, ostensibly you know what's happening everywhere. This is what sold me on being a math major, because I started off as a chemistry major. I didn't like the lab, so that was the first sign. Here was the second sign, pun intended, because this is the Maclaurin series for the sine function. I still get goosebumps thinking about it. This blew me away. Now, at the time, did we have Desmos? No. We barely had graphing calculators. You couldn't really see what was happening here. So I just had to try to imagine what was happening. That's pretty wild. Of course, round-off error gets to it at some point. It can't do it, but in your mind, that's what's happening. This is something you should remember. Now, here's what's going to help you. All you have to remember is this. It's an alternating series. Sine itself is an odd function, right? And it's all the odd powers over the odd factorials. So that's something. I put that on a note card just to know. All right, let's look at the next one. F of x equals natural log x, centered at a equals 1. Now, this would be an honest-to-goodness Taylor series because we're not centered at 0. You follow? We can't center it at 0 because the natural log is not happy at 0. But once again, I make this table. And once again, it's make the table. When in doubt, write it out. Now here we're looking at the center at 1, so I want all the information at 1. K factorial. So the coefficient, and then the term then. And here, I'm not multiplying it by just x, but x minus what? Okay? So, once again, whatever makes sense to you to organize it is fine. So once again, the 0th derivative means you didn't take the derivative. You just start with natural log x. What's the derivative of natural log x? 1 over x, a.k.a. x to what power? minus 1. Take the derivative x to the minus 1 minus x to the minus 2. Take the derivative of that. That's going to be 2x to the minus 3. Take the derivative of that. That's going to be 6x to the negative 6x to the minus 4. Take the derivative of that. That's 24x to the minus 5. Take the derivative of that. Negative 120 x to the minus 6. Take the derivative of that. 720 x to the minus 7. Okay, and once again, maybe you don't need to go down 7. Now I take each of these derivatives and I plug in the center. The center here is 1. What's the natural log of 1? 0. Plug 1 into there. You follow? And now I divide by the factorials. 0 divided by 0 factorial is 0 over 1, and that's 0. 1 over 1 factorial is 1. Negative 1 over 2 factorial is negative a half. 2 over 3 factorial is 2 over 6, which is what? A third. Negative 6 over 4 factorial is negative 6 over 24, which is minus a quarter. 24 over 5 factorial is 24 over 120, which is a fifth. You follow? And then, 0, and then you got your x minus 1 to the first, minus a half, x minus 1 squared, a third, x minus 1 cubed, minus a quarter, x minus 1 to the fourth. Are you seeing a pattern, folks? And once again, you just do enough of them to get that pattern. So let's fire up the old Taylor series here. Be 0, be x minus 1, minus a half, x minus 1 squared, plus a third, x minus 1 cubed, minus a quarter, x minus 1 to the fourth, plus a fifth, x minus 1 to the fifth. And once again, how can you test yourself? Can you see what the next one's going to be? It'd be what? Would it be plus or minus a sixth, x minus 1 to the sixth? Okay, now we try to write it using our notation. And by and large, the Taylor series, they're going to have them starting at k equals 0. That's just how they do it, because that's how all the power series stuff is phrased. Let's start at 0. Let's see if we can figure out what this is going to be if we start at 0. So first thing is, there appears to be no fraction out front. In fact, there is. I could, if I wanted to be pedantic, I could write this as 1 over what? 1. Okay. And then notice, what's the other pattern you see? The number here matches the what? You with me? It's not written but 1. Sometimes you got to go further down the line to kind of see what's going on. All right, so let's see if we can figure this out. I'm going to have an x minus 1. The power is going to match the denominator. But if I'm starting at 0, this is 0 plus 1. This is 1 plus 1. This is 2 plus 1. So if I start at k equals 0, this is going to be k plus 1. And then the denominator is also going to be what? K plus 1. And then once again, it's alternating. And we'll start with an exponent of k, and then we'll see if we have to adjust it. When k equals 0, it gives me positive, negative, positive, negative. Once again, folks, what's the ultimate check that you've got a formula that works? When in doubt, do what? Write it on out. You with me or not? Okay. So let's fire up Desmos and see what happens. Because once again, the partial sums of the Taylor series are the Taylor polynomials. Technically speaking, the nth degree Taylor polynomial is the n plus first partial sum of the Taylor series. Because if you go out to x squared, you've got the constant linear x squared. That's 3 terms, so that would be S3, even though it's the second degree. Does that make sense? It's because we start at 0. Whatever. All right, let's fire it up. Take that n back down there. So we're looking at natural log x. We're going to call this t of x now because it's a Taylor series. That's the same. It's x minus 1 in there, the k plus 1, and then there's no factorial. There it is. Boom. Okay, let's check this out. We are near x equals 1. Do we care about negative values here for natural log? Nah. We don't care about that. And then why should we find? Okay, here we go. Ready? So there's the first term there. Ooh, look, there it is. There's your tangent line. Here we go. Okay. Now, it seems stuck where? That's 1. This is what? That's 2. Now, why is that? What do we know about any power series? Any power series only works at an interval centered at the center. The center here is what? 1. We know that the natural log has a vertical asymptote at 0, so it can only converge 1 unit to the left, which means it can only converge what? 1 unit to the right. Okay? And in fact, this is the same series we had for natural log. Well, if you watch the video from yesterday, this is the same series you got by going through the geometric derivation and then integrating that. You with me? Okay? You get the same series, and that's the uniqueness of representation. So no matter how you go about this, if you're having a series representation for a function, it will always end up being the power series. Always end up being the Taylor series. Okay? And so it's good from 0 to 2, including 2, not 0. All right. How do we actually go about proving the Taylor series is going to add up to the function? We can certainly watch Desmos and we could see the wrapping happening. Is okay, that seems pretty good. But how do we know that it's actually going to work everywhere? Well, we go back to our friend, the remainder theorem. So this is what we did on Monday. We've got the old remainder theorem. Remember, the remainder theorem is just another manifestation of our friend, the mean value theorem. You can get the remainder theorem by a combo of integration by parts and the integral form of the mean value theorem. And it says that if you take the difference between the function and the Taylor polynomial, which in the language of series, we're looking at the difference between the sum and the partial sum, then it's going to look like the first thing that you didn't add in. You with me? So it has that very alternating series test feel to it. So all you got to do, right, if you think about it, if I want to show that f of x is equal to the limit as n goes to infinity of Pn of x, the way to do that is to show that the limit as n goes to infinity of f of x minus Pn of x is what? If you want to show that these go to here, then that means their difference has to go to where? 0. You with me or not? And to show this goes to 0, that means you got to show that the remainder goes to 0. Which is the same as showing that the absolute value of the remainder is going to 0. And so we would use Taylor's remainder theorem to express the remainder like that. And then maybe figure out, what's going on with that and show that goes to 0. So that's how we're going to show that these series converge to the actual function. So for example, with the sine of x, if I look at any derivative, what pops out from sine? You either get sine plus or minus, or you get plus or minus what? When you take derivatives. You either get sine or cosine. It doesn't matter which one you get. It doesn't matter what number you plug in, because sine and cosine are always trapped between what two values? So its absolute value always less than or equal to 1. You follow or not? So if I look at the remainder theorem for sine, check it out. That numerator is always 1. So for sine of x, the absolute value of the remainder for any value x, which would be some derivative at c over n minus 1 factorial. The center was 0, so it would be x minus 0 to the m plus 1 for some c between 0 and x. But the derivative here is always bounded by 1. So this is always less than or equal to the absolute value of x to the n plus 1 over n plus 1 factorial. And so now, if we look at the limit, as n runs off to infinity, of the absolute value of x to the n plus 1 over n factorial, n plus 1 factorial, remember, we're taking a limit on who here? We're taking a limit on what? N. We're not taking a limit on the x. The x is fixed. You with me? So what do we know about powers of x and factorials? Who eventually wins? Factorials eventually win, right? Because even though early on, let's say x were like 100. And I'm taking like 100 to the 10th power over 10 factorial. This is 10 factors of 100 divided by 10 times 9 times 8, blah, blah, blah. You with me or not? So early on, the powers are going to be winning. But then eventually, when like n gets up to whatever, now we're going to be multiplying by numbers, factors bigger than 100. So eventually this goes to 0, which proves that the Maclaurin series actually equals sine of x. So this is the kind of argument you have to go through to actually put in equals between your function and your Taylor series. So what we've done right now is we've actually shown that for all x, sine of x actually equals x minus x cubed over 6 plus x to the 5th over 120 minus x to the 7th over whatever 50, 40 plus minus dot dot dot. In other words, sine of x actually equals the sum. K goes from 0 to infinity, minus 1 to the k, x to the 2k plus 1 over 2k plus 1 factorial. That's because the remainder goes to 0. Okay? Functions who are equal to their Taylor series have a special name. They're called analytic functions. So if you add up to your Taylor series, you're an analytic function. And boy, things are good. Things are good when you have analytic functions, because that means you can approximate them to any degree of accuracy with your Taylor series. Now, it might not be the fastest way to approximate stuff, but it will always work. Okay? So that's pretty wild. Once again, how I remember sine, it's got all the odd powers. It's an alternating series with all the odd powers and all the odd factorials. Okay? Now, you might think, well, wait a minute, Stitzy. Are you telling me there are functions out there that have perfectly good Taylor series, but they don't add up to the original function? And the answer is yes. And this is the classic example. It's in your book. So I didn't make this up. This was the example that I learned back when I was in school. let's graph this function. Notice it's a piecewise function. That's your first clue that something's a little wonky. Okay, let's think about it. As x gets close to 0, what's going to happen to x squared? Well, it doesn't matter if x is coming into 0 from the right or left. You're plugging in very small numbers that are plus or minus, but those small numbers are going to get squared, and you're going to end up with an even smaller what kind of number? A smaller positive. Now you take 1 over x squared. That's going to become a really big what? Positive. But now if I take negative 1 over x squared, that becomes a very large negative. And what's e to a very large negative? Very, very small positive. You follow? So basically that the exponential is decaying to 0. But let's check it out. Once again, I want to look near 0 here. Let's look at f of x equals. Let's just do the exponential part. Okay, so there it is. There's that function. As x goes to infinity, you're getting e to the 0, which is 1. So it spends its whole life between 0 and 1. Okay, but look what's going on at 0. It's very extremely what? Flat. Here's how flat it is at 0. If you fire up the old limit definition of derivative, you can prove that every single derivative at 0 for this function is 0. You with me or not? Now, what's going to happen to your Maclaurin series if every single derivative is 0? It's just going to be 0. You with me? Which converges everywhere. But does it match the function? No, it only matches the function at what point? The center. So here's an example where you've got the Maclaurin series of x would just be the constant 0 function. But the Maclaurin series of x only equals the f of x only at the center 0. Okay? That's why it's a big deal, and that's why we take time to show that those remainders go to 0, so we know we can use those approximations. Okay, something we mentioned here, uniqueness of representation. When we went through and did that series for the natural log, it matched what was done on the video when we got it from a different scheme. If the function equals the power series, notice the equals here. So if in fact you have an analytic function, then those are the coefficients. Follow? So all the functions we had, you can recover derivative information. Even if we don't know what the function adds up to, even if we don't know what the power series ends up being, we know all the derivative information because those are coming from the coefficients. All right. So we got this, and we proved it. We got this is our series for the sine function. Let me just write it out here. Okay. What if I wanted to get a series for cosine? Well, one way I could do it is I could go in and I can make a table of values for cosine. You follow? Or I can leverage what I know about power series. What did we learn yesterday about power series? The calculus of power series goes term by term, right? What's the calculus relationship between sine and cosine? How can I get to cosine using calculus if I start with sine? I can do the what? I can take the derivative. I know that sine is equal to all of this. And what did I learn yesterday? How do I take the derivative of power series? I take the derivative of each what? I can go term by term. So I can either add all this up and then take the derivative, which is what this says, or I can just take the derivative of each individual term, and then add them all up. That's term-by-term differentiation. So let's do it. What's the derivative of x? 1. What's the derivative of x cubed over 6? That'd be 3x squared over 6, which is x squared over what? 2. What's the derivative of x to the 5th over 120? That'd be 5x to the 4th over 120, which is x to the 4th over what? 24. What's the derivative of x to the 7th over 5040? 7x to the 6th over 5040, which would be x to the 6th over 720. In general, if I take the derivative of negative 1 to the k, x to the 2k plus 1 over 2k plus 1 factorial. Remember, the derivative is with respect to what letter? X. As far as x is concerned, all the k stuff is just a what? Constant. What's the derivative of x to the 2k plus 1? 2k plus 1, x to the what? 2k plus 1 minus 1. We all good with that? So what's going to happen? I just got x to the 2k, and what happens with this 2k plus 1? Cancels, so I'd have minus 1 to the k, x to the 2k, and remember, 2k plus 1 factorial is 2k plus 1 times 2k minus 1, blah, blah, blah. That's your 2k factorial. So it's an alternating series that's got the even powers over the even what? Factorials. Okay? So 0 factorial, 2 factorial, 4 factorial, 6 factorial. You see the pattern or not, folks? So here is what cosine is. Once again, worth remembering. Even powers over even factorials. And I don't need to bother screwing around with the remainder on this because I know if sine x equals this, I know the derivative of sine is the derivative of that. You with me or not? That's what we learned yesterday. There are no endpoints to check because it works everywhere. So once again, this would be one you put on a flashcard or something. This is for all x. All right, let's find a series for e to the x. And prove it converges for all x. So once again, finding the series means making the table, plugging the numbers in, looking at the pattern. Proving it works means we have to look at the remainder. All right, so let's look at f of x equals e to the x. They want the Maclaurin series. Maclaurin means we're centering things at what? 0. Let's make a little table. This won't take long, I don't think, because look at the function we're doing. And once again, we're centering things at 0. So it would be x minus 0 to the k, or just x to the k. But this table is going to get awfully boring. Because what's every single derivative of e to the x? E to the x, e to the x, e to the x, e to the x, e to the x. Which means the derivative evaluated at 0 is always what? 1. So it's 1 over 0 factorial, 1 over 1 factorial, 1 over 2 factorial, 1 over 3 factorial, 1 over 4 factorial. You with me or not? So I got 1 times x, a half times x, a sixth times x, x squared, a 6 times x cubed, a 24th times x to the 4th. And by golly, isn't this the same series we had yesterday? Remember we had this series, we took the derivative, we got the same series back. It could have been really any multiple of e to the x. It turns out that actually was e to the x. So, once again, without jumping the gun, we know our Maclaurin series for e to the x is this. Now, unlike sine and cosine, which are alternating, is this series alternating? No. So no negative 1 we need there. Unlike sine and cosine, which either have just the odd powers or the even powers, e to the x has what? All the powers. And if I look at the denominators, like sine and cosine, the denominators are all the corresponding what? Factorials. So this would be just x to the k over k factorial. And yesterday we proved that the interval of convergence was all real numbers. So I know this thing converges everywhere. You with me or not? But what I didn't do is go through the remainder analysis because I didn't know that this was actually e to the x. I suspected that's what it was. It could have been 2e to the x for all we knew. So we got to look at our remainder. Whoops. So to prove e to the x actually equals this, we got to show that the limit as x goes to infinity of the remainder is 0 for all x. So I go to the remainder theorem, Rn of x. Once again, the remainder theorem looks like the first term you would leave off. But except instead of plugging the center in, we're plugging in some value c, where c is between 0 and x. That's what it looks like. So we have to think about what's going on here. Now, the good news is what? The good news is I know the derivative of e to the x. Every single derivative of e to the x is what? E to the x. So this is just going to be e to the c times x to the n plus 1 over n plus 1 factorial. Is everyone cool with that? Now, c is between 0 and x. So let's think about, if x is positive, we know the exponential function does this. You follow? So if x is positive, then I could bound what goes on here by e to the x. You follow? If x is negative, then I could bound what's going on over here by 1. You with me or not? So the bound on this is either going to be e to the x itself or it's going to be 1, depending on where x is. You follow? Worst case scenario, it's one of these. But I have e to the x, x to the n plus 1. But I'm still dividing by what? So who's going to eventually win here? Because here is x factors of e, and then I got n factors of x. Factorial will eventually dwarf both of them. Does that make sense or not? So factorial eventually wins over both of those things. So that's going to go to 0. And there we go. Now we have a series for e to the x. Now, if there is one series you remember from this course, this is the one to remember. When I took graduate analysis, which calculus grows up and turns into analysis, and analysis grows up into real analysis and complex analysis. When I took real analysis, the book we used, in the it wasn't even like paid, it was in the preface. The preface literally said, this is the most important function. Now, the reason why it was using z's instead of x's is because we were looking at it as a function of a complex variable. They said they just defined this to be the function exp of z. And then they proceeded within a paragraph to get all of the important numbers, 0, 1, I, pi, all came from this. Okay. So I thought that was interesting. Anyhow, what can we do with this now? So now we've got series for some of our classics. We've got series for e to the x, sine x, cosine x, natural log x, and then of course we also have one for inverse tangent from yesterday, right? So we've got, I mean, look at these. We got all kinds of things. Plus we got all the geometric series nonsense we could want. Let's see what kind of nonsense we can do with this. So we'll do example 4, and then example 5 is the video. And then we'll stop there. So this is where we'll stop. We'll pick up with example 6 on Monday. Okay. All right. Remember this character? The hyperbolic sine, the sinh of x, depending on what version of engineering you go into, this may be the sine that you spend your time with. The thing about those hyperbolics, sinh and cosh, is they looked hauntingly similar to sine and cosine. They behave very similarly with calculus. Like you start taking derivatives of this. Derivative of sinh is cosh. Well, let's look. The way sinh is defined is it's e to the x minus e to the minus x over 2. So I want to come up with a power series representation for sinh. Well, good news. I know a power series representation for e to the x, and I know how to do stuff like this from what we did yesterday. You follow? So let's write this down. Once again, when in doubt, write it out. Let's just write down e to the x. That's going to be 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24 plus x to the 5th over 120. Plus blah, blah, blah. Okay? Once again, the series for e to the x, kind of easy to remember because it's all the powers of x divided by the corresponding factorial. That's it. It's x to the k over k. Don't forget about k equals 0. Get that 1 in there. Okay, think back to yesterday. How do I get a series for e to the minus x then? What was the theorem? All I got to do is everywhere I see an x, I got to plug in what? So I'd have 1 minus x plus, now if you plug in minus x there, what's going to happen? It's going to get squared away, become positive. What happens when you plug the negative x in there? Negative. What happens when you plug the negative x in there? Positive. What happens when you plug the negative x in there? Negative. You with me or not? Now while we're at it, let's throw down what cosh is. Because cosh is written that way. And now we can see, since this series converges on the entire real number line, we know that it converges absolutely, right? That was part of what the ratio test told us. The fact that it converges absolutely means that we can do all this arithmetic term by term. So instead of taking e to the x, e to the minus x, subtracting them and dividing by 2, we can do that individually with the terms. So let's figure this out. What would be e to the x minus e to the minus x if I did things term by term? So I'd be taking the top line minus the bottom line. Let's see what would happen. I would get 1 minus 1, which is 0. I'd get x minus negative x, which is how many x? 2x. I'd have x squared over 2 minus x squared over 2, which is 0. I'd have x cubed over 6 minus x cubed over 6. That would give me how many x cubed over 6? I'd have x to the 4th minus x to the 4th, which would be
0.
X to the 5th minus negative x to the 5th. That would give me what? 2 of them. And then I can just sweep in and then divide by 2 when it's all said and done. So what happened to all the 2's I had? Well, once again, property of convergent series. Instead of adding everything up and then dividing by 2, I can divide by 2. I can distribute the half to every single term, which means every single one of those 2's, what happens? They cancel out. So check this out. Here's my formula for sinh. It's x plus x cubed over 6 plus x to the 5th over 120 plus, what would the next one be? X to the what? 7th. Do you recognize these denominators? Those are all what? Factorials. So this would be 7 factorial. So check this out. This is pretty wild. This is just all the odd powers of x divided by the odd factorials. What does that remind you of? Isn't that kind of like sine? But what's missing? So look at sine. What's missing? This one isn't alternating. Isn't that wild? So remember when we talked about absolute convergence, we would take the series and then look at the absolute values, you know? You take those coefficients, take the absolute values, look, we're just getting that. Anyone want to guess what the pattern for Cosh is? We could just go through and, because Cosh are just adding them. What happens here? These, all the even powers double up and all the odd powers do what? Drop off. So I guess what Cosh is. Cosh looks like cosine except it's not alternating. You getting goosebumps yet? There's something going on here. This is completely wild. We'll talk more about that on Monday. So now, do you kind of see why sinh and cosh are looking like sine and cosine? Because at looking at it through this analysis, you can see that they're somehow deeply connected. Right? You just make them alternating, and then all of a sudden you go from the hyperbolic functions, you make them alternating, now you're back to the circular functions. And that's pretty wild. Because one of them is, I mean, literally, how do you define the sine function? You got to draw the unit circle, and then you got to measure your real number in radians, and then you got to look at where it intersects the unit circle. That's how you've defined the sine function, right? This is complete geometric construction. How do you define the hyperbolic sine function? Oh, it's this, right? Pretty wild. All right, what's in the video? And then we'll talk about the take-home and stuff. So here, what we do, using series for sine, cosine, e to the x, find the first few non-zero terms of the following. E to the minus x cosine 4x. So you can get a series for e to the minus x, get one for cosine 4x. How do you multiply them together? Well, that's what the video tells you. It's basically like an infinite foiling problem. You just distribute, because absolute convergence says you can do that kind of thing. The tricky part is you want to make sure you're collecting up the like powers of x. Okay? So make sure you're collecting up the like powers of x. And I know how much you folks enjoyed long division, right? I know how much you enjoyed that. Well, get ready for really long division, because you're dividing two infinite polynomials to get the series for tangent. So once again, that's worth your time. All right. Speaking of really long division, remember this was kind of the this is what got us started in all of this mess. Was this one here? Right? This was that geometric series formula. This is what got us started way back. It was like 2 weeks ago when we were just starting on geometric series. Remember, the problem was, hey, what values of x makes this converge? And then we ended up graphing. I was like, oh, that's kind of wild. So you can actually get this by doing division. You can actually get this by doing long division. You ready for this? What times 1 gives you 1? 1. What's 1 times 1 minus x? Now we subtract. I get x. What times 1 gives you x? X. Multiply. Subtract. What times 1 gives you x squared? You follow or not? So if you believe in your gut that long division works forever and ever, you can actually derive that series using long division. I think this is your grandpa's favorite way to get this, by the way. Ask your grandpa about that.